Okay, so for this week, we are going to learn the second type of classification technique, which is called a naive Bayesian. Naive Bayesian is a classification technique that are based on conditional probability. So we have explained the principles of naive Bayesian in our lecture slides. So far we have learned two types of classification. One is decision tree, we learned it last week, and this week we are going to learn the second type. So after we learn these two types, one thing you probably want to ask is, which one is better? So the answer is, it depends. So I'll show you how to compare these two types of classification methods in this week's tutorial. So the application for this week's tutorial is for vote prediction. So we have two datasets as usual. So one is for training. So we use this training dataset to build our model, either naive Bayesian model or decision tree model. And then the second dataset is called a prediction dataset. So we have some missing variables that needs to be predicted by other existing attributes. So the application of this case has very practical meanings. So for example, here we know that each congressman, whether they're Republican or Democrat, and also their historical vote for different types of bills. And then using all these voting result and their party, we can use that to predict some of the missing variables for education spending bill, which is a target bill that we want to predict, because we have still have 35 congressmen whose voting data is missing in this prediction data set. If the total of yes votes exceeds 172, that means we can pass this bill, otherwise we cannot pass. So if you count all the yeses here in this existing data, we have 155 yes. So that means we need to have at least 17 additional yes for us to pass this bill. So that's basically the background of this case. And so as usual, we are going to import our training data into RapidMiner first. So this is our training data, and we use comma as a column separator, and then we keep everything as default. Then we just connect that with the result, and we run the data import section, and we check the statistics here. It shows that for education spending bill, so far we have 155 yes vote, and we have 216 no, and 29 abstain. So that is the summary of our data. So as I said, in order to have 172 yes vote, we need at least 17 additional yes. So now this is our training dataset. So using this training dataset, we want to build our either decision tree model or naive Bayesian model. So let's try decision tree model first. So we use set row, and then we select education spending as the label for our prediction model. And according to the lab tutorial, we are going to first build a decision tree model. And then we connect them. Now we are ready to generate a decision tree. But since we have learned the pruning and also Gini index, so for this time, I want you to play with the parameters here for decision tree models. So even for the same data set, for the same prediction variable, if we set up the parameters differently, we will have different decision tree models. So according to the lab tutorial, we are going to use Gini index for this time, and we are not going to apply any pruning, and then we can say split the minimum is going to 3, 3, and let's run this decision tree model. And this is the decision tree that we are going to generate. So as you can see here, this time the decision tree are not as trivial as we get last time for the flower case. For each of this decision node, we have the majority of yes and some no's and some abstains. And here the majorities are no's or some yeses and some abstains. So it's similar for all the rest of them. And then we can go back and change this to 10 and 10, minimum leaf size and a minimum size for split, which means when we achieve a node that are less than or equal to 10 nodes, then we are not going to divide it anymore. So you can expect less leaf node. As you can see here now, we are only having just one node as our decision tree. So we can also do some further changes here. Let's change it back to 20, and now you can see again this is just a party as the discrimination between the decision tree node. So for different parameters, we have different decision tree models. So for a real life data set, we have to try and error and use different parameters to see which decision tree can give us the best performance. So I'll discuss about the performance a little bit in today's tutorial, and then next week we will continue to discuss about the performance of data mining techniques. So for here, for now, you just need to know that we can configure the parameters for all the data mining techniques that we have learned. And this is the first step for a decision tree data mining. And then the second step we're going to do is we need to import the second data set, which is the prediction data set. So this is our data set for prediction, and we want to predict the mixing variables here for this education bill. And after we import the data, we also want to set the rule because we want to the system know that the education spending is going to be our prediction variable. And then we are going to apply the model that we have already built, and then use that to predict our result. So that's labeled, and we can also show the model that we have built. And then we can run this result. So I forgot to change back the settings. So the settings should be gain ratio, and the minimum size for split is 4, and the minimum leaf size is 2. Then I'm going to run this again, and this is my decision tree, and this is my prediction result. So let's go into the statistic view because it allows us to see this clear. So now you can see the prediction variable education spending based on this decision tree model. We are going to have 18 no's and 16 yes vote and 1 abstain vote. So that means we have in total 171 yes vote. So that means we cannot pass this bill based on the voting result prediction for decision tree model. And that's the decision tree part. Since we have learned a new method called naive Bayesian, now we can replace the decision tree model with a naive Bayesian. So naive Bayesian operator, then we link it, and we just use that to replace our decision tree model. So remember that we are going to use the Laplace correction here, and then we can run the naive Bayesian classification model. And now you can see the new result, and if you check the statistics here, now the answer has been changed. We have 17 no's and 17 yes, and 1 abstain, which means we have a better chance of passing this bill. And according to the prediction result here, that means we can have 172 yes votes for this bill. So based on this example, you can see that the different data mining techniques may give us different results based on the data. So which one is better here? So in order to answer this question, we need to look at the statistics of the confidence. As we have explained last week, confidence basically means how confident are the algorithms in terms of telling yes or no's. So here, if we look at the confidence here, so most of them are either zeros or 100% or more than 95%. And here, most of them are same thing. And let's go back to the decision tree model. So let's try to bring back our decision tree model. And minimum leaf size is going to be 2. And let's look at our decision tree model. And if you look at the confidence level here, similarly, we still have a lot of very high confidence, very low confidence, and a very high confidence and low confidence. So here, possibility of 0 means our confidence of saying no is 0. In the opposite way of saying this is our confidence of saying yes is almost close to 100%. So we want a lot of zeros and 100%, but we don't want something in between, because if something is between, that means we have 70% or 30%, that means we are not really sure. If it's 50%, it's like almost flipping a coin. So the algorithm cannot tell us anything about the prediction. So in this case, if we compare these diagrams with the diagram we have seen earlier in the naive Bayesian algorithm, we have more observations in the middle here in this area. So that means this algorithm is not performing as well as the previous algorithm, which is naive Bayesian. You can also look at the deviation and average. So this one has a smaller deviation. So smaller deviation means all those confidence values, they are closer to 0.5. If this division is bigger, that means we have more values in the two ends, not in the middle. So that's why the bigger the division is, then the better the performance it is. So that's why in this case, naive Bayesian is better. Okay, thank you for watching. That's all for this week.